Hi all, this is Dr. Shanti, working as professor in the Department of Electronics and Communication Engineering, R.M.K. College of Engineering and Technology, affiliated to Anna University, Chennai. This presentation is about signals and their types. Contents. This presentation is going to talk about introduction of signals and types of signals. Introduction of signals. Right, now let's start with the introduction of signals. One animation is shown here. It just shows how a signal will look like. The animation here, what you are seeing is a continuous time signal. Right, now let us know what is meant by a signal. Right, signal is nothing but that is any physical phenomenon that is happening in nature can be represented in terms of one or more variables, right? That is going to be the actual definition of a signal. Right now, in order to know the definition of signal better, we have to know about two variables. One is called as the dependent variable, the other one is going to be called as the independent variable. Right now, here the time t is going to be called as the independent variable, and the amplitude or the voltage that is represented along the x-axis is going to be called as the dependent variable. Right, now why the amplitude of the voltage is called as a dependent variable is its value at any instant of time. That is, you are specifying the value of the voltage only with respect to time, right? Say at 0 the amplitude of the voltage is 0. Say at this point the amplitude of the voltage is maximum. Once again at this instant of time the amplitude is minimum, so that is 0. Right, here it has a negative maximum. Right, and now once again at this instant of time it is 0. Right, so the amplitude at that is, you specify the value of the amplitude or the value of the amplitude is specified in terms of time. So that is why we call it as time as independent variable and voltage as dependent variable. And a signal is always specified in terms of independent and dependent variables, right? Now let us look into the actual definition of a signal. As I told you already, that is, any signal conveys information on the nature of a physical phenomenon, right? So this physical phenomenon will be represented as a function of one or more, that is, it can be represented as function of one or more independent variables, right? Next, now let us consider that is the speech signal itself, right? Now how do you represent speech? Speech is nothing but acoustic pressure with respect to time, right? Now there are two variables here. One is the acoustic pressure, the other one is time, right? Now what is the acoustic pressure? That depends upon the distance the wave travels, right? So the dependent variable is going to be the acoustic pressure, and what is the independent variable? The time, right? So that is how you represent, say for example, a speech signal is represented mathematically by acoustic pressure as a function of time, right? Now, based on the dimension, you can classify a signal as one-dimensional, two-dimensional and three-dimensional. As I told you, any signal will be represented in terms of with respect to one or more independent variables, right? If a signal varies with respect to one independent variable, it is a one-dimensional signal. If it varies with two independent variables, then it is two-dimensional signal. Or that is, if it is varies with more than two independent variables, then I'm going to call it as a three-dimensional signal. Right, now one-dimensional signal is nothing but a speech signal, daily rain, that is annual rainfall at a place, daily maximum temperature, right? See here, and the best example is the variation of a voltage or a current with respect to time. So this is a one-dimensional signal. this example for a two-dimensional signal is an image, right? Example is going to be a two-dimensional. That is, example is a two-dimensional signal is nothing but an image where you're going to have that is time and space coordinates, right? And the third one is going to be space, time, and depth also all coming into play, right? So this is going to be an example for three-dimensional signal, right? Now let us see the basic types of signals. There are two basic types of signals which you will be encountering in our day-to-day life. The first one is a continuous time signal. The other one is the discrete time signal. Right now, as the name indicates, let us look into the waveform. When I look into this waveform, x of t is the dependent variable and t is the independent variable. Here, x of t is defined for all values of t, which means that at every instant of time, for every instant of time, you will specify the amplitude, right? Say what is the amplitude at every, say at this time x of t has a value of this, right? At this instant of time it has a value of this. At 0 the value say might be 2 or 3, right? Whatever is the maximum value, right? So if a signal is defined for all values of t, such a signal is going to be called as continuous time signal. The next one is going to be discrete time signal. Here the time index variable is n here, correct? The time index variable is n. Here what is the time index variable in CT signal? CT signal, the time index variable is t, and t that is, it can have all fractional values, which means that it can be 0, 0.25, 0.5, 0.75, 1 and so on, right? So it can take all fractional values. Whereas in the case of discrete time signal, look at the waveform first. Here you represent x of n. X of n is the dependent variable and n is the independent variable. Here you see the value of x of n. Your x of n has been or it has values only at discrete instance of time. For example, when n is equal to 0, you will have a particular value. When n is 1, you have a particular value. When n is equal to 2, you have a particular value. When n is equal to 3, you have a particular value. So only at discrete instance of time, x of n is specified, and hence the name discrete time signal. Whereas here x of t is defined for each and every instant of time, right? And hence it is called as a continuous time signal, right? Continuous time signal. As I told you earlier, a continuous time signal is defined for every instant of time. That is, a signal that is defined for every instant of time is a continuous time signal. Examples, the best example is speech signal. Speech signal is a function of time. Atmospheric pressure as a function of altitude are all examples of continuous time signals. And it is denoted by x of t, where t can take any value from minus infinity to infinity, right? That is few more examples: human voice, TV signal, analog phone, record player. All these are examples of continuous time signals. Best example is a sine wave, a cosine wave, right? All are continuous time signals, right? And an animation is shown here that shows you a continuous time signal. Discrete time signal, right? The same way, if a signal is defined only at discrete instance of time, right? Say stock market index, there might be, they will specify the values in the morning at one fixed time, might be at 10, then at 12, then at say 5. So at discrete instant of time, if they are going to tell. The same way, the temperature recordings of a city, they will find out at say at 6 o'clock, at 10 o'clock, at 12 o'clock, at say 3 o'clock, at 6 o'clock. So all these are examples of discrete time signal. Here discrete signals are continuous in amplitude or discrete in time, which means that only for discrete instance of time you specify the amplitude. right? It is obtained by sampling a continuous time signal. Now I'll show you an animation for sampling in the next slide, right? That is switching. The easier way to understand is just switching on and off that is on turning on and off a switch is an example for sampling. When you on, you'll get your circuit is corrected, that is you'll get a 1. When the switch is off, you don't get the output, right? So that will be the example for sampling. I'll show you in the next slide. Examples for discrete time signal. Now everything is a discrete time, digital, right? Computers, digital phone, right? See here, look at this waveform, the bottom waveform. The bottom waveform is when the torchlight is on, you get a 1. When torchlight is off, you get a 0, right? Here it's a continuous waveform. You get a continuous output for with respect to time. Here you see it is going to be discrete one, either 1 or a 0, right? So that is a discrete time signal. Sampling. What a sampling is? It is the process by which a CT signal is converted into DT signal. Say for example, x of t is your continuous time signal and x of n is your discrete time signal. When I close the switch, whatever is the input will come at the output. When I open the switch, this input will not come to the output, right? So we get that is you give the input as a CT signal, you get the output as a discrete time signal, right? And what is this T? T is nothing but the space between the samples, right? Now to understand better, right? Now this is the CT signal what you give, correct? This is going to be your CT signal, right? Now what is the output you get? For the same input signal, you get the output this way around, which means that for that is only at discrete instance of time I get it, right? Now what is the time between the samples? That is the time between the samples is nothing but your capital T. That is what is shown here. And what is n? This is nothing but n. Right now, where do you take the samples? At t is equal to 1t, 2t, 3t, 4t, and so on. So that is what is shown here, right? And here is an animation. When I press on the switch, you get the output, right? And when I off the switch, I don't get the output, right? That is what is shown.